Okay, today we are going to be talking about gears and gear train design in tutorial. And we're going to start with a bit of a review since we just recently covered gears in the lectures. And I think a quick review of some concepts could be helpful. So that's what we're going to do first. So, quick review. And this will be important stuff to know for the current problem set 7, which is a practice problem set. It's not graded. The solution's available for you there, but I definitely recommend going through those problems because, as Professor Diller said in the last lecture, there will definitely be a question on gears on the final. So it would be a good idea to have some practice on gears so you know what you're doing going into that. So let's do a quick review first. The first concept we're going to review is the speed ratio. And I'm just going to write this as EJI, where J and I fill in for some other numbers. And usually the way we write our speed ratio is as the output speed of some gear train divided by the input speed. And in other words, we could write it as omega j over omega I, where j is the output, I is the input. And a convention that is often used when we look at the speed ratio is we say that the speed ratio is greater than 0 if both shafts spin in the same direction, and we often say it's less than 0 if they spin in opposite directions. So what do I mean by that? Well, I'm going to draw a skeleton diagram here of two external gears. So these skeleton diagrams were covered in the last lecture. So here's one gear. And here is the other gear, connecting to it like that. So these are the shafts of the gears here and here. So if this one is rotating this way, then this one is going to rotate in the opposite direction, because at this contact point here, they have to have the same speed since they're in contact with no slip. So for this one, it's going into the page at this point, which means that this gear must also be going into the page at that point. Now, the thing about drawing your rotations like this on your skeleton diagrams is that sometimes it can be a little hard to parse, like what does this one actually mean in terms of the rotation? So what I like to do personally is I like to use arrows to represent the vector direction of our rotation. So what I mean by that is I'm using right-hand rule, and I would write my omega as an arrow coming like this, pointing along the shaft axis there. So if this is our omega input, then this will be our omega output, or sorry, our omega j, to use the same nomenclature. So for this one, I'm taking the right-hand rule. So I point my thumb in the direction of the arrow, and then my fingers curl in the direction that the gear is rotating. So if this one's rotating this way, you can see my fingers are curling into the page on the right-hand side, which means that on this side, it must be going in the opposite direction, curling into the page like that. So this is a handy way to keep track of the directions that your gears are rotating, especially if you start to get large gear trains that might have many gears with like bevel gears. So imagine you have something like this, where you have a bevel gear that connects to another bevel gear, that connects to another bevel gear like this, which might be like a rear differential in a car, as an example. So here you have 3 gears, and if you're going to draw, the rotation of all of these, it can be a little hard to keep track of. but we know that this one, let's say, has some rotation that way. Then this one is going to have a rotation like that. Again, using right-hand rule, we can see that with this rotation, it's a little hard to move. It's like this. So my thumb's pointing in the direction of the arrow, my fingers curl into the page, so we can see the velocity of that point is down into the page, which means that for this one, the velocity must be down into the page, so that's why the arrow is pointing that way. And then for our last one, we can see that for this one, my fingers are down on the left side, so it must be coming up on the right-hand side. So that means that this is my direction here, using the right-hand rule. So we get something like that. So this is a way of keeping track of your rotations in your skeleton diagrams, and it's a little more meaningful than just using this E greater than 0 or E less than 0. So this works fine if you're dealing with a simple gear train, but when you're dealing with more complex gear trains with bevel gears and things like that, I recommend you use this method where you're representing each of these omegas. Let's say this is omega 2, this one here is omega 3, and this one here is omega 4 for gears 2, 3, and 4. I find that can be a little helpful for keeping track of this. Are there any questions about, we're going to get more into the speed ratio in a moment, but are there any questions about determining the rotation directions of gears? Yes?
Can you explain the right diagram one more time?
The one on the right here? Yeah, this one's like a set of bevel gears. So it's going to be hard to draw in 3D. But maybe if I draw like a section diagram instead, it might make a little more sense. So we have 3 gears in contact like this, 1, 2, and 3. And they have teeth on the sides like this. These are bevel gears, which was a type of gear that was covered in the lecture yesterday. So a bevel gear looks something like this, where it has some sort of angle instead of being just a spur gear would look something like this instead, where it has straight teeth on the sides. Whereas a bevel gear is designed to have some angle, which might be, in this case, it's 45 degrees, that allows us to transmit motion to shafts that are pointing in different directions. So these shafts are not parallel. So here we have 3 gears. This is gear 2, this is gear 3, this is gear 4, each of them mounted on their own shafts. And if gear 2 is rotating this way, and I'm using vectors to represent rotations. We use the right-hand rule. We put our thumb in the direction of the vector and then curl our fingers in that direction. So we can see that it's rotating that way. So if that's the case, this point here on the gear is headed into the page. So if it's headed into the page here, there's no slip between these 2 gears. That means this gear is also headed into the page on this side. So it's going in here. You could use maybe an X to represent that it's going into the page. And it's coming out here. So there's like a dot there to represent it's coming out of the page. So in that case, this is not the right direction. We want our hand going into the page. Our fingers curl in. If we're wrapping around the shaft with our hand, the fingers are going in on this side. So that means that the vector direction is downwards. So we would write the direction like that. And then for the last gear here, gear number 4, again, we're thinking about the same thing. So I said it's going into the page here, it's coming out of the page there. Both gears are in contact, so this one must also be coming out of the page there. So you could use a dot to represent that. It's going into the page up on this side. So in that case, our fingers are going into the page. When we curl around that shaft, they're going into the page that way. So that means that my thumb was pointing in this direction, so that's the direction of rotation of that final gear there. Is that a better explanation? Does it make more sense now?
Yeah,
okay. Any other questions about determining the rotation directions of gears in more complex diagrams like this? Okay, and there is an example problem in the homework that does something like this with the more complex gear train, so take a look at that. and the solutions are already available online. So these would be an example of bevel gears. Okay, so let's now that we've talked about a very complex example, let's go back to something simpler and just talk about an external gear pair. So in this case, we have something like this. I could use my circle templates very approximately. Maybe we have a gear like that. And then is something exciting happening? Is it just that these circle templates are fascinating, or? Okay, so here we have two gears. Oh, I see. It's a little hard to draw freehand. It's okay if you just want to sketch some random circles. The details aren't critical. I just want my notes to be nice and neat for you when I upload them online. After the tutorial, these notes will always appear online on Quarkus. So if you ever want a copy, that's where you can find them. Okay, so I've drawn omega 2 and omega 3 in opposite directions because we know that at their point of contact here, there's no slip. So they share some pitch point velocity Vp, or pitch circle velocity. And I've drawn just a simplified version of the gears where this is the pitch circle of the gear. So I don't have to draw their teeth, which are pretty complicated to try to draw accurately. So we're just going to represent this, the gears like this. There's no slip between the gears. And that's why we can say that at this point, they both share the same velocity Vp. So to prove that, to show how we derive our gear ratio, which this was covered in lecture, but we're going to review it real quick. The magnitude of that pitch point velocity is going to be equal to omega 2 times R2, because this gear is moving at some constant speed, omega 2, and it has some radius here, R2. And this one has some radius here, R3. And we know that at that point, because there's no slip, the velocity is the same. So it's also equal to omega 3 R3. That's the magnitude. And so bearing in mind that this is how we've defined our speed ratio as output speed over input speed, let's say that this is our output gear and this is our input gear. This one here's our input, this one here's our output. Then we could say that our speed ratio E32, the magnitude of that speed ratio is equal to omega 3 over omega 2, which we can get by rearranging this equation up here. So if we bring omega 2 over to this side, so divide both sides by omega 2, divide both sides by R3, then we get R2 over R3. So that's the magnitude of the gear ratio, the speed ratio is just the ratio of their radii. So this is something that I see every year, that when I'm doing this, people forget. They kind of swap these around. So you'd say like omega 3 over omega 2 is R3 over R2. That's not right. So the bigger gear, in this case, is omega 3. It's going to spin slower than the smaller gear, which is omega 2. So the only way that that's going to work is if you put the larger radius in the bottom. Do you know what I mean? So what I'm trying to say is this is coming from the math here. We're rearranging these values here. So this is the true statement. But like if you ever want to sort of check yourself, think about which gear is bigger. The bigger gear should turn slower. If the bigger gears, like if we wrote this as R3 over R2, then we'd end up with the bigger gear turning faster, and that's not going to make any sense physically. So that's our speed ratio there. And usually, like I said above here, we would write it so that it's less than 0 if the shafts are turning in opposite directions, which is true in this case. They're turning in opposite directions. So we could write this as E32 without the absolute value signs is negative R2 over R3 because the shafts are turning in opposite directions. Now, where this changes is if we have an internal, external gear pair. Okay, so again, I'm going to use my circle templates. I'm sorry. I know this is a little hard to follow along quickly on your page. So let's say that it looks something like this. Okay, so the way that this looks is that this gear is actually a ring. This external gear is a large ring, like that. That's our internal gear. They contact at this point. So here's the point of rotation of the larger gear. It has some pitch radius, R3. This is our smaller gear. It has some pitch radius, R2. Like that. And we're going to do the exact same analysis so we can see that they contact at this point. So there's some pitch circle velocity, VP. And they share it at that point. So that means that if omega 2 is going that way to correspond to this VP, then, so this is gear 2 here, this is gear 3 here. Then gear 3 must be going in the same direction because they have to share a velocity at that point. So this is our omega 3 direction. So in that case, it's a similar analysis. We have the absolute value of VP is equal to omega 2 R2 because it's some radius R2 and it's moving at a speed omega 2. And it's going to be equal to omega 3 R3, like that. So we get exactly the same expression for the magnitude of our gear ratio. We have omega 3 over omega 2 is equal to R2 over R3. So same expression as before. However, if we were to write without the absolute value sign, we often would say that this is positive R2 over R3 because the shafts are spinning in the same direction. So positive. So that's an example of an internal-external gear pair. Yes, question?
So you, when calculating these ratios, you'll always find the magnitude first and then manually find the direction in terms of positive and negative?
Yeah, I would recommend manually looking at the diagram and trying to think about, okay, what's the pitch velocity at this point given the rotation rate of the gear that we know, and then propagate that through your diagram by saying, okay, they share a velocity at this point, so this one must be going in this direction if that's on this side. Yeah, I would recommend going through manually. And that's similar to what we were doing up above here. So that's my recommendation. However, what I will just show you in a moment here is that for simple gear trains where all the shafts are parallel, sometimes you just need to think about, okay, external pairs, negative. Internal, external pairs, positive. And you can just use those numbers to work through the gear train and you'll end up with sort of the right values.
Is that always the case?
For a simple gear train where all the shafts are parallel, yes. Yeah, you can just use positive and negative. But I would recommend for anything where you start to have non-parallel shafts, always do it manually, just in case. Because in this example, you might think, okay, this is an external pair, so it's a negative ratio. This is an external pair, it's a negative ratio. Negative times a negative is a positive, so 2 and 4 must be spinning in the same direction. But that's not true, they're actually spinning in opposite directions. So that's why it's important anytime you have non-parallel shafts, do it manually. Think about what the speed is at each contact point, the direction of that speed, and then work through it that way. That's my recommendation. Does that answer your question?
Yeah, thank you so much.
You're welcome. Any other questions about what we've covered so far? Okay, so let's quickly look at a simple gear train. And this is actually the technical term, is a simple gear train as opposed to a compound gear train, which we'll do on the next page. So for a simple gear train, again, I'm just going to use my circles. And these don't really matter. You can draw them whatever you want. So maybe there's one like that. And then there's another one like this. Maybe another one like this. And then one like that. Oops. The last one has a defect. Okay, something like that. So here we have gear 2, gear 3, gear 4, and gear 5. And we're just going to do a bunch of external gear pairs. So if you were given R2, R3, R4, and R5, and asked to find the speed ratio, and let's say that's omega 5 over 2, where 5 is our output, 2 is our input. So that's omega, oh sorry, this is not, this is E. E5/2, that's our speed ratio, which is omega 5 over omega 2. So we could work through our problem. We know that omega 5 over omega 2, we're going to have to think, how does the speed get from 2 over to 5? Well, we're going to have some ratio omega 3 over omega 2 multiplied by some ratio omega 4 over omega 3 multiplied by omega 5 over omega 4, like that. So the omega 4s are going to cancel, the omega 3s are going to cancel, and we're going to be left with omega 5 over omega 2. And the reason I'm doing it like this is because given what we've just done above, the examples we've done above, we can do each of these parts individually. We know that omega 3 over omega 2 is negative R2 over R3. We know that omega 4 over omega 3 is equal to negative R3 over R4. And we know that this part here, omega 5 over omega 4, is equal to negative R4 over R5. So let's put all that together. We get omega 5 over omega 2 is equal to negative R2 over R3, negative R3 over R4, negative R4 over R5, like that. Well, we have 3 negatives, so negative times a negative is positive, times a negative again is another negative, so we know our final answer is going to be negative. R3s cancel, R4s cancel, we're left with negative R2 over R5. Wow, that was a lot of work to come up, well, not that much work, but what I mean is it was quite a bit of work to come up with the solution that it's just equal to negative R2 over R5. Okay, so what we've just revealed here is that these gears here, 3 and 4, they have no effect on the speed ratio. All that matters in a simple gear train, and a simple gear train is when we have a bunch of parallel shafts like this, and each gear is on its own shaft. For a simple gear train, it's just the radius of the input over the radius of the output. Done. And in terms of finding the direction, you just count up the number of pairs. We have 1 pair, 2 pairs, 3 pairs. So gear 2 to 3 is 1 step. Gear 3 to 4 is 1 step. Gear 4 to 5 is 1 step. It's an odd number, so therefore we have a negative speed ratio. If we didn't have gear 5 here, if it was just 2, 3, 4, we would find that 2 and 4 are rotating in the same direction. And so we would get R2 over R4, and it would be a positive, because negative times a negative gives us a positive. So we can draw this in to keep track of our omegas. Here's our omega 2, omega 3 in the opposite direction. Omega 3 is this way, so omega 4 is that way. Omega 5 is this way. So we can see omega 2 and omega 5, opposite directions. Okay, so for simple gear trains, so this is a technical term, simple gear trains. That's where we have each gear on its own shaft. Let me just move this up a little. And all shafts are parallel. In this case, the speed ratio depends only on the size of the input and output gears. Okay, the intervening gears make no difference. Yes, another question.
We don't really care about the fact that the gears themselves, even like their shafts are parallel, but they're not on the same like horizontal axis. Like one shaft might be here, one shaft might be here. That's okay.
Yeah, that's okay. Yep, because all that matters is there's some radius here to this point, there's some radius to that same point. And similarly here, it's that radius to that point, that radius to that point, and then like that. So it doesn't matter if they're all on the same plane, because we're only worried about them 1 pair at a time.
And because there's no slip, like it'll have the same velocity at that one contact.
Exactly, yeah.
Okay, cool. Thank you.
You're welcome. Yeah, so it doesn't matter. They don't need to all be, like their shafts don't all need to be on the same line. Like I've drawn here, they could be all on sort of a zigzag pattern like this. Doesn't matter. You're only concerned about the input and the output gear. I will say the direction, so I should say here the magnitude, just to be absolutely clear, the magnitude of the speed ratio depends only on the size of the input and output gear. The direction depends only on the number of gears. So in this case, we had an even number of gears, so it comes out negative. If you have an odd number of gears, it'll come out positive. Okay, any other questions about simple gear trains, calculating the gear ratio? Okay, so the last really quick thing that I want to talk about before we move on to a problem that'll be something like what you're going to see on the problem set is that we can define the sort of gear type, or the gear, it's not really a type, I guess, a certain measure of the gear. And these were covered in lecture. We have the circular pitch or circumferential pitch. This is PC, lowercase pc. which is pi d divided by n, where d is the pitch circle diameter. And n is the number of teeth. We can have a diametral pitch. Diametral pitch, P, which is defined as n over d, same n, same d as before. Oh yeah, and this one has units of inch. This one here has units of per inch. And then we have something called the module, which is d over n. And these are often reported in units of millimeters. So all of these measures here, the circular pitch, the diametral pitch, and the module, they are all measures of the same thing. Because you can see it's the ratio of d over n. This is multiplied by pi. This is n over d, so it's 1 over the ratio of d over n. So they're all measuring the same thing, which is essentially the tooth spacing on the gears. And for two gears to mesh, they must have equal tooth spacing. In other words, say PC2 is equal to PC3, or equivalently, P2 equals P3, that's a capital P, or equivalently, M2 is equal to M3. Okay? And we can use these measures here, the circular pitch, the diametral pitch, and the module, to come up with an alternative expression for the gear ratio. So for an external gear pair, we said that, so this is for an external pair. We said that E32 is equal to negative R2 over R3, which is the same as saying negative D2 over D3. The ratio is the same. And we could write D2 as being, say, M2 times N2, and D3 as M3 times N3. So that's just replacing D with M times N, rearranging this equation for module. We know that if the gear's in mesh, then M2 is equal to M3. So that means that they cancel. And we're left, oh, sorry, there's a negative sign there. We didn't drop that. Well, we did for a moment there, but we caught it. That gives us negative N2 over N3. So instead of using the gear radii or the gear diameter, we can also just use the number of teeth, which is really handy because the number of teeth we know is going to be some integer number, and it'll be reported for whatever gear you have. So sometimes this makes it a little easier to track your calculations for the gear ratio because you're just dividing one integer over another integer. It makes things quite handy. And as we'll see in the design problem, representing our gear ratio as the ratio of the number of teeth can be helpful for finding valid solutions to our gear design problems. Because, again, you can't have a gear with a non-integer number of teeth. That doesn't make sense. A gear can't have half a tooth. It would not mesh properly. So we're going to see how that affects our design problem in just a moment. Any questions about measuring the tooth spacing on a gear and how that's relevant to the gear ratio?
We
Yes?
could do the
Uh-huh.
substituted that in. We could do the same with the circular pitch or diametrical pitch, right? Knowing that the pitches have to be the same so they maybe cancel out or something.
Yeah, absolutely. You could use any of these measures. I used M, but you could have used P. You could have written here that D2 is equal to N over P. And you could write that in, and then you would have a P2 in the bottom, P3 on the top. They would cancel because they're equal. And you could do the same thing with the circular pitch. The pi's would cancel immediately, and the PCs would cancel as well. So it doesn't matter which one you choose. I like using module because it's our metric one in units of millimeters. But you can use whatever you want. And often the problem will give you one of those three measures. It'll either give you module, circular pitch, or diametral pitch. And it's important to stay in those units because if you buy imperial gears, the chances of them meshing with metric gears are pretty slim. I don't know, they might make some metric gears that have like some strange module number that like equates to some value in inches. But usually if you buy gears in inches, they're only going to mesh with other imperial gears. So whenever you start a problem, whichever one they give you, either the metric units or imperial units, I recommend you stick with those units for the whole problem. Yeah. You're welcome. Any other questions? Okay, let's get into a design problem. And when we reach the top of the hour, as always, we're going to take a break. So that's another 12 minutes away or so, 13 minutes. So we've been talking about simple gear trains. What about a more complex case that was talked about briefly in the lecture of compound gear trains? I guess this is compound gear train design specifically. So we're going to be given the following diagram here. We have some shaft with a gear on it, like that. So this is a skeleton diagram. And then that connects on to some other gear which is on another shaft here. And that one connects to another gear here on the same shaft. And then we have the output shaft here. Like that. And we're going to number these gears. Oh, one thing to mention as well is that these shafts are collinear, the input and the output shafts. And they're some distance apart. That distance is often labeled C. And we're going to number our gears. This is gear 2, this is gear 3, this is gear 4, and this is gear 5. And we're going to say that all gears have a module of m equals 2 millimeters. And the distance C is going to be equal to 180 millimeters. Now, I'm going to attempt to draw this a little bit in 3D here. It's going to be a pretty shoddy attempt, but I'm going to give it a go. So here we have our small input gear, our bigger gear on the side there. It has some shaft coming out of it that connects on to another gear over here. And that connects to our output shaft here. So this is our input shaft, and there's our output shaft like that. So this is gear 2, that's gear 5, this is gear 3, this is gear 4. It's something like that. I don't know if that helps visualize it at all, or if that's just confused the mess even more. Okay. And we're going to be asked to find, first, part A, the equation for E52, so that's our speed ratio, our input-output speed ratio, with respect to N2, N3, N4, and N5. That's the first thing we're going to be asked for. And the second thing we're going to be asked to do is actually design the problem. So we're going to be asked to find N2, N3, N4, and N5 such that our speed ratio, our input-output speed ratio, the magnitude of that speed ratio is equal to 0.25. Okay. So in the next 8 minutes, I think we can solve part A, and then we'll take a break, and then we'll come back for part B. And we're going to do this out by hand, and then I will show you that I have a program that will do this for you automatically, that you are welcome to use if you should wish to do so. But for something like your projects, but I always recommend doing the calculations yourself, because saying I just plugged it into a computer program and it gave me the answer is not going to get you many points. So keep that in mind. Okay, solution time. Actually, before I get to the solution, are there any questions about the problem statement? Great. Okay. So E52 is omega 5 over omega 2. And once again, I'm going to break it down, which might seem a little tedious, but I'm going to break it down into its individual components here so we can think about each part. This is a compound gear train. So we have, starting from 2, we have omega 3 over omega 2 multiplied by omega 4 over omega 3 multiplied by omega 5 over omega 4, like that. Okay, so these are simply some external pairs here. So 2 and 3 are an external pair. So that's pretty simple. We've done that before. And I'm going to use, because we've been asked to find with respect to the number of teeth, that's what I'm going to use for our gear ratio. So here we have so how about let's just find the absolute value in this case. So we have for omega 3 over omega 2, that's N2 over N3 from before. So I'm just finding the absolute value in this case. So this is really the absolute value of this times the absolute value of that times the absolute value of this. Okay, so we have that. And now we have something we haven't seen before. These gears, 3 and 4, share a shaft. They're rigidly fixed to one another, so they must share the same rotation rate. You can't have one rotating at a different rotation rate, because then you'd be shearing the shaft in the middle here, or bending it or twisting it somehow. So we're going to assume, everything is rigid. So in that case, we have this rigid body. There, 3 and 4 are connected together. So that must mean that that gear ratio is just 1. Omega 4 over omega 3, they're equal to one another. Omega 4 is equal to omega 3 because they're on the same shaft. So that's why we can say here that omega 4 over omega 3 is just 1. And then finally we have omega 5 over omega 4, which again, this is just an external gear pair between 4 and 5. And we have N4 over N5, like that. Because for external gear pairs, remember we have omega 5s on top, so that means we have N5 on the bottom. So I'm just using the same expressions that we had before on the previous pages. So given that, we have the absolute value of E52 is equal to N2, N4 over N3, N5. Now the question is, in this case, we could give it like a positive or negative number if we wanted to. So I'm going to do my previous analysis that I would do before. So I'm going to draw an arrow in here along the shaft to represent omega 2. Omega 2 and omega 3 rotate in opposite directions. So that means that omega 3 is this way. Omega 3 and omega 4 are on the same shaft, or gear 3 and 4 are on the same shaft. So that means that their rotation rates are the same direction. So this is our omega 4. So I've just drawn the same arrow as over here. I've drawn it in the same direction on this side. So that means that omega 4 and omega 5, they're an external pair. So that means that omega 5 must be this way. So we could say in this case then that the gear ratio is positive. Yeah, so that's what we could say in this scenario. But I think that it's best, instead of worrying about positive and negative gear ratios, when you're dealing with compound gear trains, anything that isn't a simple gear train, don't worry about positive and negative. Just take the magnitude and say that, you know, for this case here, omega 2 and omega 5 spin in opposite directions. So you could say omega 5 direction and omega 2 direction marked on diagram, or indicated, perhaps is a better word. Indicated. There we go, on the diagram. Because perhaps positive and negative start to lose their meaning when we have a bunch of different shafts involved. Okay? So there we found E5 over 2. And we've noticed that unlike in the case of the simple gear train, these intermediate, like intervening gears, 3 and 4, actually do matter to the resulting gear ratio. They do make a difference to its magnitude. So this is something to bear in mind with these compound gear trains compared to the simple gear train that we did before, where we had the same number of gears, but we found that 3 and 4 didn't matter. We just ended up with R2 over R5 in the end. That's not the case here. More complex expression. Any questions about how we found the speed ratio for this gear train? Okay, great. You seem confident. Let's take a break. We'll come back at 11:10 and we'll work on the second part of the problem, which is the design problem. And I'll be here to answer questions if you'd like to come down to the front in the intervening time. Okay, we're going to get started again. Let's settle in. All right, let's start the design portion of this problem. And I've seen a design problem similar to this on exams in past years. I think you do have access to previous year's exams. Professor Diller is going to share with you some previous exams, so you'll be able to see some of the gear design problems that have been present on past finals. Okay, so for part B, we're going to have to think about what the constraints are on our design. And a crucial constraint in these compound gear trains is the distance c of 180 millimeters. We need to make sure that our gears are actually going to fit in that space that we have between those two shafts. So in that case, we have the gear 2 has some pitch circle radius here, R2. Gear 3 has some pitch circle radius, R3. And similarly for gear 4 and 5, we have some radius R5 and some radius here R4. So if R3 plus R2 was greater than C, then our gears would not fit. They would collide with one another. You wouldn't physically be able to push both gears into the space. If R2 plus R3 is less than 180 degrees, your gears aren't meshing. They're probably not even going to be touching. They're just moving next to each other. There's going to be no contact, no force transmission. That would really suck. Completely ruin the purpose of your design. So as a result, we can say that R2 plus R3 is equal to C. And also, R4 plus R5 is also equal to C. So this is a crucial constraint for our compound gear train design. Whatever selection of gears we come up with, we need to make sure that the radii give us C. The other thing that we need to keep in mind is that the number of gear teeth has to be some positive integer. Okay? It has to be some positive integer. You can't have a negative number of gear teeth, and you can't have a non-integer number of gear teeth. Like I said before, that doesn't make any sense. You can't have half a tooth on a gear, especially on a spur gear like this. It doesn't make any sense. Not sure what happened there. Okay, you can still see I've lost my monitor here. Okay, we'll just roll with it. Okay, it's back. Having all kinds of trouble with this system today. Okay, so we need to make sure that our gear teeth are an integer number, positive integer number, and we need to make sure that these constraints are satisfied. So what I'm going to do is I'm going to rewrite this constraint in terms of the number of gear teeth. And in this problem, we've been given a gear module. All gears have m equal to 2 millimeters. So I'm going to use that. We know that m is equal to d over n. And we know that r is just 1/2 d. So we can rewrite this expression above as c being equal to 1/2 m2 n2 plus m3 n3, like that. And similarly, we could also write that that's going to be equal to 1/2 m4 n4 plus m5 n5. Gears 2 and 3 are in mesh, and well, in any case, we were already told that all gears have m equal to 2 millimeters. So this is all the same m. So we could just write it as m, and we can bring it over to the other side, and we can see that 2c divided by m is equal to n2 plus n3, which is equal to n4 plus n5. So there's two equations here. We have n2 plus n3 is equal to 2c over m. We have n4 plus n5 is equal to 2c over m. Okay. So I'm going to insert our values for 2c over m. We have 2 times 180 millimeters divided by 2 millimeters, which gives us 180. Okay, this is a good sign that 2 times c over m gives us an integer number. If it didn't give us an integer number, there'd be something wrong with the problem, or maybe we made a mistake before now. Because we have two positive integers adding together, they have to give us another positive integer. It's impossible otherwise. So this is a good sign to have some positive integer for 2c over m. Okay, so let's write out our constraints. We have equation number 1, n2 plus n3 is equal to 180. Constraint number 2, n4 plus n5 is equal to 180. And constraint number 3 is that our speed ratio n2, n4 over n3, n5 is equal to 0.25. So here we have three constraints, but we have four unknowns. Sorry, I was going off the page there. You can always yell at me when I do that. I'll just cry a little bit. So therefore, multiple solutions. Multiple solutions to the problem, because there's only three constraints, but we have four unknowns. 1, 2, 3, 4 gear teeth, or 4 numbers of gear teeth. Yes, there's a question.
Didn't we say in part A that that omega 4 over omega 3 is 1? So wouldn't that imply that n4 is equal to n3?
Yeah, that's a good question, actually. Someone else asked me that during the break, and maybe I should have elaborated before I got there, because that is a bit of a point of confusion. Okay, so the question was, we said over the break that omega 3 and omega 4 are equal, so shouldn't that mean that n3 and n4 are equal? Well, the reason we would say that, that the ratio of the speeds is equal to the ratio of the number of gear teeth, we say that for a specific circumstance. We say that for meshing gears. So this is an external-external gear pair. They're meshing together, transmitting speed that way, and then we can say that their speed ratio is the ratio of their radii or the ratio of their number of teeth. Similarly for an internal-external gear pair. But both of these scenarios, we're describing a case where gears are meshing with their teeth. This is not that scenario. So here, when the gears are on the same shaft, they're not meshing with each other's teeth. So this gear could actually be a completely different gear. Like we have, all gears have m equals 2 millimeters. We could technically have these two gears sharing some module and these two gears sharing some module. It wouldn't matter in the problem as long as these two are sharing and these two are sharing. So we have two gears that are on the same axis. It's not meshing. So the ratio of the speeds has no impact on the number of teeth on either gear. So that's why we have that situation here. You're welcome. Any other questions? Okay. So here's our three constraints and four unknowns. We have multiple solutions. So how are we going to go about solving? Well, we're going to have to choose one of our gears arbitrarily. And I like to make that the input gear usually. And if we're going to choose arbitrarily, we might think, well, we can pick any number between 0 and 180. But that doesn't really make sense either because, gears can't have 0 teeth. So maybe we'd say, okay, we could choose any number from 1 to 180. Well, that also doesn't make sense. I mean, what's a gear with 1 tooth? What does that look like? Right? So usually, for practical reasons, we have some minimum number of gear teeth on a given gear. And I see a variety of numbers. I think it's pretty normal for that to be 12. But you might be given this on a problem, and it might say, assume the minimum number of gear teeth is 17 or 15 or whatever. And that's the case in the homework. But if it's not told to you, 12 or 10 is a pretty safe assumption for the minimum number of gear teeth. So in that case, we know that our maximum number of gear teeth on any of these gears, since the sum has to be equal to 180, is going to be 180 minus 12, which is equal to 168. So we can arbitrarily choose any number between 12 and 168 for our gear teeth. Okay, so we're trying to achieve a gear ratio of 0.25. So we want to scale down, but maybe for the first stage from 2 to 3, we don't need to scale down at all. So maybe we just make that a 1-to-1 ratio. That's a perfectly acceptable answer. So we're going to choose arbitrarily. We're going to choose N2 is equal to 90 just arbitrarily. Arbitrarily. I can spell most of the time. Okay, so in that case, we can insert N2 equals 90 into our equation 1. And we get that N3 is equal to 180 minus 90, which is equal to also 90. Okay? And then we know that we can take equation 3 and insert our values for N2 and N3. So this is equation 3. Let me move this up a little. We can insert these values for N2 and N3 into equation 3, and we get N4 over N5 times 90 over 90 is equal to 0.25. So that tells us that N4 is equal to 0.25 times N5. We can insert that. So these were both inserted into equation 3. Then we can insert this expression into equation 2. So we have 1.25 times N4 is equal to 180. And if we do the math there, we divide 180 by 1.25, we get N4 is equal to 144. And N5 is equal to 180 minus 144, which gives us 36. Okay. Now, before we give our final answer, I highly recommend... Oh, yeah, there's a question. Oh, yeah. Thank you. That's a good point. So this is 0. Yeah, this should be N5. Thank you for catching that. N5, N4. Yeah, thank you. Very good catch. Okay, N5 is equal to 144. N4 is equal to 36. Okay, so before we give our final answer here, let's just double check to make sure that this gives us the right speed ratio. We have E52 is equal to 90 was our N2. N4 is 36. And here's 90 and 144. And that should give us 0.25 exactly. But you can double check my numbers there. Okay, and for these problems, because we're kind of all over the place when we're putting in when we're writing down our various numbers, I would recommend that you write your final answer at the bottom of the page like this. N2 equals 90, N3 equals 90, N4 is equal to 36, N5 is equal to 144, and then put a big old box around it. Make it easy for the marker to find. Okay, so this is one possible solution, and it gave us exactly what we wanted for our output, which is 0.25. Now, what would have happened if I chose something different? Like instead of N2 equals 90, I chose something like N2 equals 89. Well, chances are our numbers would not have worked out quite so nicely. We would still be able to come up with an answer for N3. N3 would be 91 instead of 90. And when we would plug that in here, we would have 91, or sorry, we'd have 89 over 91, and that would give us some nasty value here that would give us n4 is equal to some number times n5. And we'd probably end up, in that case, with a non-integer solution for n5. That's totally fine. We just need to choose to round that value. So I would recommend if you go through this process, you should get immediately, you would choose an integer number for n2 that is guaranteed to give you an integer number for n3. And then when you get to this point, it may end up that this equation doesn't equal exactly 144. It might give you like 143.2. I would just recommend rounding the number because the final answer has to be an integer. So if this gave you 143.2, just round down to 143. And then similarly for n4, then we're like, if n5 is an integer, we're guaranteed to get an integer for n4. Okay? So just do round up or down, your choice. And that's going to give you some value that isn't going to be exactly equal to 0.25. It'll give you an approximate solution, but that's okay. Usually on these gear train design problems, we'll ask you to get the desired gear ratio to within some number. So we would say to within the nearest decimal place, or to within 0.01 or something along those lines. So if you have to do some rounding, that's totally fine. The thing you have to make sure though is that your gear teeth are integer numbers and the sum of the gear teeth for meshing pairs is equal to 180 for this particular problem. Otherwise, the gears won't mesh, they won't fit into the desired space. Okay, so that's one solution to the problem. Another solution that actually gives you exact numbers would be like n2 is equal to 60, n3 is equal to 120, n4 is equal to 60, n5 is equal to 120. So there's other exact solutions as well that you can find. So that's how you do the problem manually. But I actually have written a MATLAB code, which you can find on the tutorial page. And I'm just going to show you quickly how that works. So I recommend using this MATLAB code to explore solutions. So here's the MATLAB code. You can find this on Quirkus. So I wrote this a little while ago. Here's that gear train that we were dealing with there. And you can insert whatever you want for the gear module, whatever you want for the shaft spacing. And here's the minimum allowable number of teeth. Let's say it was 12 for this problem. And find the number of teeth on each gear for a speed ratio of this. So for our problem, we did 0.25. Hit run. And it gives you this plot. And this plot will tell you all the solutions for giving you a value of 0.25. But some of them are inexact solutions. So everything on this line is an inexact solution. So here we have a solution for n2 and n4. So let's say, we can't quite get on the line because it has to be an integer number. So if we chose 63 for n4, 63 for n2 and 57 for n4, then that would give us an approximate solution. However, I have these circles here that indicate solutions that give you exactly 0.25. So if you choose 60 for both of these, if you choose n2 is equal to 90 and n4 is equal to 36, and I only report two of the gears here, right? N2 and n4. And the reason that I only report two is because the other two gears are just 180 minus those numbers. So it's quite simple to get your solutions from there. So you can use this to see exact solutions and pick them out. So 0.25 has a lot of exact solutions. That's why I chose it for this particular example problem. But what if we had something weird like 0.271? In that case, there are no exact solutions, but the code will automatically highlight for you the closest inexact solution, which in this case was this point here, where N2 is 27 and N4 is 109. So you can use this code if you want, and there's other inexact solutions that are elsewhere. And you can use this code if you want to explore designs. You can use it for your homework. But if you're using it on the homework, I recommend, it's not a graded set, so it doesn't really matter. But I would encourage you to try these problems the way I've done it in tutorial. Do it by hand, because you won't have this code on the exam, right? So use this code as a way to examine these values. The other thing that I want to show you is very often real gear trains don't have exact numbers for their gear teeth. So if you look, this is for a Honda Civic, which is one of the most common cars you're going to find on the road, seemingly for the past several decades. And here you can look at the gear ratios in their transmissions. And we can see that their gear ratios are seldom exact numbers. So, so again, you can see here that second gear gives you a ratio of 2, but it's not exactly 2. It's 2.08. So it's really not a big deal that you have these hyper-specific gear ratios in these problems. If we ask you to find gear ratio of 2 to within some value, then just find it to within, say, 1 decimal place, and that's fine. The other reason for why they choose it this way is to have reduced wear on their gears. So something you can think about here. Let's try the Photos app and see if it works. So here's an example of a spirograph. I don't know if you've ever played with these as a kid. They used to have them at my elementary school, and we'd draw all these cool patterns. And what I'm trying to show you with this particular example here is that this red tooth here and this blue tooth here, you can see that every second rotation around, this red tooth is contacting this blue tooth. And the number of times that a tooth comes into contact is a function of the gear ratio. And there's some complex equations that you can use for that. But generally speaking, what you'll find is that if you use, say for the outer gear, the larger gear, if you use a prime number, then you'll find that the number of times that the teeth intersect, that the same teeth touch one another, is going to be a lot smaller than if you choose the outer gear to have some multiple of the inner gear's teeth. So every time a gear tooth contacts the same gear tooth, if there's some defect on one of those teeth, you're going to keep rubbing that defect into the other tooth, and it can result in increased wear. So the nice thing about choosing a prime number for the larger gear is that we have that wear spread out over as many teeth as possible, as opposed to focused on an individual tooth. This isn't critical. It's probably not going to come up on your exam or anything, but I think that it's an interesting real-world sort of consideration to think about when you're designing your gear teeth. Anyway, that's everything I have for you today. The notes will be online. The MATLAB code is online. And I'll put the Honda Civic online as well, so you can take a look at that. Yeah, thanks everyone.